So hello, am I audible? Someone please confirm so that. Okay, okay, thank you. Okay, okay. Join. So good afternoon, everyone. So today we would be okay. Now it's fine. So today we would be mostly focusing on the week three part. Week three, what the courses, the part portion that has been covered in week three of the smart grid course that is going on. So previously, what we have discussed, I think most of you are aware. Uh, okay. So previously we had the discussion the last week or last to last week. We mostly focused on the smart grid, how the smart grid works, the basics, the background of smart grid, and why the grid is becoming smart, and what are the associated things that needs to be considered to make the grid smarter. So based on that, the basic overview that we have given from the course itself we have got, and last week we have also discussed how the monitoring part and how the monitoring objectives needs to be fulfilled. So anybody has any question regarding those things? If you have any questions, then you can ask. We can discuss on those things for some time, and then we would be focusing more on week three, some basic overview of week three, and then we would go for questions and all these things. But before that, if you have any questions, then how these monitoring objectives needs to be fulfilled, what are the things that needs to be associated to make the grids more smart, anything. If you, so this week mostly The part was mostly related to the storage devices or the battery energy storage devices. So, okay, then let's start this part only. So, mostly our focus was mainly to think more about smart grids, right? So, what are the objectives that were to be fulfilled? Now, first of all, the communication things should be more enhanced because already we have the power system layer, right? So we need to integrate the IT layer on top of that. Okay, so to integrate that IT layer or the communication infrastructure, that thing needs to be emphasized right now because we have the entire system in operation. So if we use those power system lines, transmission lines, everything, so there are the problems of threats, malicious attacks, and all these things would be focused. But for the time being, the communication infrastructure, the data acquiring devices, and their communication of those data to the master station uh, helps you or helps us all to or the helps the operators, distribution system or transmission system operators to monitor closely about how the system changes over time, right? Now, we what we know is that for any system, like let's consider for the time being, let's consider the uh, conventional power system, right, or conventional generation system. So in the conventional generation system, what we mostly take into consideration is any idea, or mostly which part of means mostly what kind of generating unit delivers uh, the major chunk of the power to serves the major load to of India. Any idea? Any, you can write in the chat box also. So mostly the energy, thermal power plants, okay, or coal based plants. So what we know is that we have large synchronous generators working there, okay. So if we take into consideration that these synchronous generators can deliver this amount of power within that stipulated period of time, then it's everything is fine. No, nothing is going beyond our assumption. So because the amount of load that has been considered, that amount of load can be rightly delivered by the generating units, then there is a good balance or losses are catered, but that's it. But uh, what we see in power system is that sudden rise or fall in load, okay. So, and one thing is that suppose we have let's consider everyone are from the same background, since from the electrical engineering background, or people from other backgrounds are also here, because mostly the thermal power system that we know, the operating system, the idea it should be clear that this is the operating system. Then this is the boiler. Then we have the turbine stages. Then we have the generator, and after that we have the transformer. Then we have the transmission line. Then we have the uh, other step. This is the step up transformer, and this is the step down. And then we have the load. Let's just consider the primary case because no need to go in the distribution side for the time being. So what we observe is that this is the generator, this is the turbine. So what we need to do is just we will be switching on or switching off the lights, anything. It's not lights only. Let's consider for the time being the high highly loaded means higher side of the loads, because not for the residential part but also consider the industrial part. So what in our control is that we would be suddenly decreasing or increasing the load as per our need. But what the power system operators needs to be focused is that they will have to maintain the frequency within a particular band. Now, to maintain the frequency within that band, otherwise the generators won't synchronize, because if the frequency don't fall within that band, the generators would not get synchronized and they won't deliver that amount of that deliver the power to the grid. So, what we need to focus is that as we go back, means here we have the load side. So switching actions or the time constants of operation is much faster. Okay, but as we go back, means here we have the lightning, here we have the generator. So as we go back, means from the load to the boiler part, so the time constants goes on decreasing. Means that what I am trying to say is that for the generator, you can increase or decrease the load as per your will, but the generator will have to give generator will take some time to ramp up. Or okay, English Hindi both. Okay, okay. So okay, so for the first time I'll discuss this thing in English, and then okay, I can. Okay, for the time being, let's discuss both the thing, both the verses. Okay. सो व्हाट आई सो बेसिकली हम कहना क्या चाह रहे हैं कि हमारे पास जो लोड है, सो जो लोड है ये हमारे हिसाब से हम लोग राइज और फॉल कर सकते हैं, मीन्स डिक्रीज और इंक्रीज कर सकते हैं। बट अगर यही लोड को जनरेटर को केटर करना है कि generator will take care of this load, so for that generator to take care of that load, it will need more injection or more steam input from the turbine side. Okay, and the generator is not that generator, means generator, the shaft of generator and the turbine are in same shaft. Both of them operate on the same shaft that rotates the rotor of the generator, right? So so when we consider the mechanical, means the amount of the mass, the rotating mass, we don't consider only the mass of the generator, rotating mass of the generator, but also that of the turbine. So what I am trying to say is that the time of operation increases as we go towards the generator side. मतलब जैसे हम लोग towards the generator जा रहे हैं, फिर उसके बाद टरबाइन आएगा, फिर उसके बाद बॉयलर आएगा। तो ये सब के लिए जितना फास्ट हम लोग लोड को चेंज कर देंगे उतना फास्ट ये लोग रिएक्ट नहीं कर पाएंगे। सो दे वोंट रिएक्ट दैट फास्ट to the load changes, means this generator, turbine, boiler, because you need to, it takes hours to change the ramp up the generators, because the steam input we need, for the steam input there are lots of procedure, it will pulverize and all these things, that input needs to be, oxygen rate needs to be balanced and all these things. So various things are there. So this sudden rise or fall is bound to happen, मतलब ये राइज और फॉल होने को ही है, ठीक है, ये पावर सिस्टम में इसको रोक नहीं सकते, बिकॉज हमारा जो विल है, हम कब बंद करना चाहेंगे ऑन करना चाहेंगे ये हमारे ऊपर डिपेंडेंट है। और ये ना ही हम किसी को बोल कर रहे हैं, वी आर नॉट, मीन्स बिफोर स्विचिंग ऑन और स्विचिंग ऑफ वी आर नॉट delivering that information to the means operator side. So they will get the information based on the data that these things have been switched on or off. Okay, so for these things, so ये sudden rise or fall होने के लिए what drawback or what contingent situations we might face? Can anybody say what are the challenges that we need to face and how those challenges are mitigated? कैसे हम लोग वो challenge को मतलब चैलेंज पे रिएक्ट करते हैं और कैसे उसको सॉल्व करने का कोशिश करते हैं। बेसिक मतलब हमारा लोड बढ़ गया है, लेट्स कंसीडर केस वन कि लोड इंक्रीज एंड जनरेटर जो अभी जनरेशन है वो जनरेशन उसी में ही चल रहा है, मतलब वो अभी इंक्रीज डिक्रीज कुछ नहीं हुआ है, जैसा चल रहा है। तो ये सडन लोड इंक्रीमेंट की वजह से क्या हो सकता है, व्हाट वुड कॉज दिस सडन लोड इंक्रीमेंट इन द एंटायर पावर सिस्टम, व्हाट limitation needs to be governments, in what those limitation needs to be taken care of by some activities. But firstly you just try to say that what will be the challenge, first challenge that we would face right now. We suppose load has increased suddenly. Anyone from you? It's just a discussion session, right? So load increase, but generator generation is same at that instant. But generation is providing the previous generating value. So we would face a frequency shift. So frequency would deviate. Frequency deviation is observed. Okay, frequency deviation हम लोग फेस करेंगे। ये frequency deviation कौन सा direction में होगा कि rise और fall में होगा? That is based on the difference between the load and generation. So based on the difference between load and generation, the frequency deviation would be observed. Okay, so if load is high, generation is low, then frequency would drop. If load is low, generation is high, frequency would rise. So for the time being, how is this frequency deviation initially mitigated? Means any idea? Any idea? Means just feel free to say anything. Means with regard to power systems, of course, but try to say at least so that we can, because the need for the battery, that needs to be uh, the basis of why these batteries and all these things, DERs and all these things have risen. That the reason behind the rise of these things needs to be understood first, and day by day the need would also get, um, the demand of these things or the smart distribution grids or smart transmission grids would get emphasized day by day. So अभी क्या है इसके लिए, जैसे हम लोग फ्रीक्वेंसी राइज और फॉल हो रहा है, जैसे इसमें फ्रीक्वेंसी F1 में ऑपरेट कर रहा है, बट बेस्ड ऑन दैट देयर वुड बी अ सडन change that would be observed, and after that AGC, automatic generation control. Have you heard the term automatic generation control? So the frequency would drop down to some point, and then there would be a disturbance pattern. After that, when with the AGC and all these things, yes. So these things would return back to again to the normal operating frequency, because by that time the generation would try to increase, the boilers rate would also increase, the governor action will take place. So now what we are aiming to do is that if this is quite a time consuming activity, right? That to make this change or to balance this deviation of the or the load and generation deviation of drift, we need to at least have some backup system that can rightly come into action or whenever needed, means, and very fast in operation. The time constant should be faster, because if one thing is operations, if loads are increased Now it's around 4:24 p.m. and the generation would increase up to, or rather it would take a time of around 1 hour to meet that demand. Now for this 30-35 minutes, the issue would be that there can be the generator which is trying to mitigate that deviation. By that time it would reach that present loading condition or present loading, that load that has changed. There would be another load shift, so things should be faster in operation. So this balance should be made faster. So for that, these storage devices, the importance of these storage devices have grown rapidly. Okay, so that's why we need battery energy storage devices, pump storage devices, but not, those are not devices, pump storage plant, oh, sorry. Okay, so okay, so anybody has any questions regarding up to this part? If you have any questions, प्लीज. हम यही बोलना चाह रहे थे कि जो स्टोरेज डिवाइसेस का इम्पोर्टेंस, दिस फॉर्म्स द बेसिस ऑफ द स्टोरेज डिवाइसेस और इंटीग्रेशन ऑफ द स्टोरेज डिवाइसेस. क्यों हम लोग स्टोरेज डिवाइसेस को रखेंगे हमारा सिस्टम पे? सो दैट these sudden deviation in frequency or the load generation imbalances would be mitigated at the earliest, and they should be fast responsive, because already we have this means we have these thermal power plants that would be responding on a larger time frame. Also now you may ask that the DERs or the distributed energy resources are also there, so won't it affect? Because you can consider that case also, because with the DERs in place nowadays, the generation, the DER, what's the basic difference between the DER and a thermal power plant or anything else, or a power plant, hydropower plant? Any rough idea? What's the basic difference that can be that that is in between the DERs or distributed energy resources and the thermal power plants or hydropower plants? Basic, basic difference, a very basic difference is based on the amount of generation or based on the generation quality, you may say. Sorry, your voice is not clear. Yes, yes, they are intermittent in nature, and that's why the point I am trying to say is that the DERs would be delivering some amount of energy as per the weather condition, as per the wind, as per sun irradiance, and all these things. So we need to take that amount of energy or power generation into consideration, the amount that would be delivered by the DERs. मीन्स DER जो हमको दे रहा है, ठीक है, उसी को ही हमको लेना पड़ेगा. We don't have any choice कि we need this much amount of demand to be fulfilled, so you increase your generation by this much, you decrease your generation by this much. So your point is correct that it is intermittent in nature. So my point is that we need to take that much amount of power into consideration with that much amount which would be given or generated by the DERs. And for the thermal or hydro, so it's based on the control actions are on our side. So the variation that we would be that is the variation in the angle of these turbines blades and all these things. If we vary based on that, the rise or fall in the generation can be take means can be control, means the rise or fall of the generation can be controlled for these thermal and this thermal or hydro and all these power plants. So conventional power plants. So what I am trying to say is that we have these thermal power plants where we don't have this intermittency, but we have the DERs. So with the integration, not only the case of last the point that I mentioned here is only based on the uh, load increase or decrease. But if you consider the case of DER means injection imbalances. So we have a entire power system with let's consider a large amount of DERs at various nodes. So the resultant, what would be the, let's suppose here you have a node or bus. Okay, so let's consider a three bus system. So here you have a bus, here you have a generator, and let's consider here you have a load, here also you have a load, but also you have a DER in place. Here it's a DER and also load. So when we calculate or when we uh, perform this load flow, so we take the power injection, right? So that power injection would be the differences between the power needed by the load and the power injected by the DES. So the resultant power that needs to be taken care of by the generator, and also definitely this P2, this is P3. So P2 and not directly P3. So what we need to take care is that P3 minus DER. This much amount of power we need to take care of for this node, bus number 3. For bus number 2, this P2 entirely needs to be taken care of, and for this is the generator is the slack bus. Let's consider it will only one single bus and three node system. So my point is that last point what I mentioned is that the intermittency caused by the loads, but here we can also see that due to the intermittent DERs, there can be this power mismatches, and the intermittency would result in sudden generation rise or fall. So for that case also this frequency deviation would take place, previous frequency deviations would take place, and those things also should be taken care by the storage devices, because if suddenly a cloud cover would be occurring in any part, so if suppose the forecast was something different, so that is also a major problem. वो भी एक प्रॉब्लम है जो पहले भी हमने बताया है कि हम लोग के पास जो जनरेटर का और जो इंटरमिटेंसी ऑफ डीईआरस एंड ऑल दिस थिंग्स ये हमारे जो है तो ठीक है, लेकिन हम लोग को स्पिनिंग रिजर्व, जो स्पिनिंग रिजर्व है, so to make the grid smarter we have associated more complications, okay, to reduce the cost of per elements per unit power consumption. Yes, our aim is to minimize the cost, but the complexity, already the power system is a very big complex human made network, and उसके साथ हमने और भी कॉम्प्लेक्सिटी ऐड करवा दी है, क्योंकि हम लोग का कॉस्ट मिनिमाइज करना है, कॉस्ट ऑफ पावर कंजम्पशन, एंड ऑल्सो ग्रीन के गो ग्रीन हमारा एम है कि हम लोग को ग्रीनर फ्यूचर चाहिए. सो कार्बन ऑक्साइड, कार्बन डाइऑक्साइड मीन्स फ्री ऑफ कार्बन. सो फॉर दैट we have to take all these things into consideration. So एनी आइडिया कि स्पिनिंग रिजर्व के हिसाब से हम लोग को क्या बैकअप में रखना चाहिए, हाउ मच स्पिनिंग रिजर्व डू वी नीड टू कीप to ensure that these intermittent DERs and all these things can be taken care of. Means intermittent changes can also be more or less it would be taken care. And what was the previous previous consideration of these spinning reserve that we used to keep when conventional power system were in operation? Any rough idea? Means these are roughly ideas that we need to discuss sometime. So that any rough idea, and what's the problem? Means we are aiming to reduce cost, but what problem we have associated? Hydro. No, but yeah, but hydro to uh, yes, it is used as spinning reserve, but I am trying to say that what would be the quantitative increment that we have uh, for the time, means for considering these renewable energy resources into consideration for ensuring that the amount required for peak shaving. Yes, peak shaving definitely, but not only peak shaving is part or based on, okay, that we would discuss that uh, the peak shaving part. But I'm trying to say is that contingency consideration, yes, all these things, yes, contingency consideration is definitely a part, but I'm trying to say is that when we have when we had these only these conventional power plants in operation during those times, the spinning reserve, because everything was controlled by humans or the operators, so they had the idea ki what would be the most at most what are the forecasting errors. So based on that things, mostly the forecast or spinning reserve was kept on an average, it was kept as 5% of the total load. Extra means on a higher side, because to sometimes there can be fall or rise or generator outages and all these things. So for that contingent situations to uh, take care of those contingent situations. But with the integration of these DERs, we have increased our spinning reserve to on an average 15%. Now 15% of the spinning reserve needs to be kept because because of this intermittency that is now in operation for the power system. So now what we can see is that there is a major change between the amount of, so here we have incurred the cost. So in order to reduce cost, we have incurred a area where we need to invest more. But that's the optimal, that's we need to find the optimal operating condition based on which the spinning reserve capacity would be reduced somewhere in near future. So for that, what should be more accurate? Means, since my question is that to encounter the intermittent DERs, the spinning reserve rise, we can see a large spinning reserve rise. But what can be done, or what activities should be more accurately done to reduce this 15% to, let's say, 10%, 5% or something, anything to reduce, at least to reduce this 15% to 10% for the time. Let's consider what things should be done properly or more accurately, what activity. It's a part of major some, we have some major parts of how these power systems work. So it's one of these major part, a major activity that needs to be performed on daily basis. Any idea? We have also discussed, not in this fashion that this is directly we have discussed, but now it's a question. Any idea? Any rough guesses? Because we need to understand the basis of the battery energy storage system. Otherwise, our aim now, you can go through this lecture. You have definitely gone through this lecture, and you have had a good idea of how these things operate. So shall I repeat the question? Question को repeat करूँ? What activity should be done more accurately so as to ensure a minimum spinning reserve capacity?
So
It's a
proper load and generation forecasting.
proper load and generation.
Forecasting, sir.
Yes, 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 yes. Not generation forecasting, but definitely load as well as generation forecasting. Yes, yes, definitely for the D years it's generation forecasting. So we need to accurately forecast. That's the correct point. So we need to forecast accurately. Means the forecasting tools should be much more developed to consider, means to reduce this amount of spinning reserve. So nowadays, what I means from my one of my friend working in solar generation power plant. So what I have heard from his side is that they need to give a 15-minute forecast, means 15 minute per 15 minutes they have to they place a means value that they would be generating for the next day. Means today, means suppose today is Saturday, so before closing of this Saturday they will have to ensure that for every 15 minutes, means if we divide one 24 hour day into 15 minutes, we will get 96 points, means 96 slabs. So all throughout this day, means for these 96 the points or 96 slabs, they need to place a value that tomorrow this would be our plant's forecasted generation. So based on that, these all these actions, means we will have to have these. Let's consider the case that if suppose we have more accurate forecasting for these uh, generation or DERs or load forecasting. So load forecasting is already there, means we can trust the load forecasting part, but the net forecasting, means load and the DER, difference between load and DER, that has become a major challenge. So what I was trying to say is that they have these 96 data points. So these 96 data points need to be filled today so that load flow and all these things, these activities like this load flow and all these things would be done priorly, so that tomorrow the line overload limit and all these things would be checked whether everything is within their threshold limit or not, and based on that this this would be the final dispatching situation scenario. So the thing is that, but that is the load forecasting or the generation forecasting, sorry, that is being done by some operators or some means a different company. They just work on the data. So these their company delivers, this is the generating unit or the solar generating unit, they delivers these real time data, historical data, yearly data, 2 yearly data, etc. to the to another company. They are expert in doing forecasting, so they just give the forecasted values. They don't tell what the procedures they use there, but they give just those 96 values, and they need to, and this company or the solar generation company need to fill up those values from their plant, that their plant would be delivering that amount of power or generating that amount of power. Now the issue comes in that that person is not sitting anywhere near, or he or she is not associated with that generation company itself, not nowhere he is or she is in that location itself. So he is or she is working just on the basis of data. So the problem rises is that whenever they also have these people, means who are working in the power plant or the control engineers, they have the authority to change values, but for that also they have some bandwidth, that for the next 15 sorry, not 15, 1 hour or 1.5 hour, they can't change the value, but you can forecast that now in your locality or in your place where you are right now, you can observe that a sudden cloud cover, a rainy day would be following. Means based on these your visual inspection, you can understand that some problem or some rain and all these things, cloud covering and all these things would be there. But the person who has forecasted for today, he or she is not at that point of time. So these people have the authority to change values, but beyond the predefined bandwidth. And that is what I can remember is that it's not less than 1 hour. Means you can change, but not any data within that 1 hour, but based on the present situation you can change beyond 1 hour, values beyond 1 hour, that if you can feel that this rain would or this cloud cover would last for more than 3 hours. So you can forecast based on the based on weather. If you, it's entirely based on you or the person who is forecasting engineer. He is also, their designation is also called forecasting engineer. So they change the values, and because everywhere there is a cost associated, because if you fail to meet that amount of generation or commitment that you have made, then you will be penalized. And again there is a case that if you have, means this is on the higher side, that if you have given this much amount of, suppose you can just take any random value, that you have committed that you would be delivering 5 megawatt, you would be delivering 5 megawatt to the grid. Now there is a threshold that you can give 10% more or 10% less, but what you felt is that there it can't go beyond, or I think for the lesser part it's around 15%. Both side that's not same. Means on the higher side if it is 5%, then on the lower side it is 15%. So you can change your value on the lower side, but if you don't meet that demand, or if you, because the generation is not on your hand, that is the solar plants would be operating on MPPT, and based on that they would be generating. So what you need to do, or what you need to do is that you should be picture perfect, means at least with some errors definitely, because all these are forecasts, but you can't give a total, or the forecast which will be very less, so that, and if that value is very less, then also you will be penalized, that because you have forecasted a very less value but you have generated much more. So your generation would can't go beyond 5% of your forecast, because then there would be a sudden imbalance, and cases do arise that people do fail in all these activities, because mostly they are presentation, can't be see presentation, प्रेजेंटेशन दिखाई नहीं दे रहा है. ओके 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 ओके. तो ये जो डिफरेंस है, इसके लिए ये इंटरमीडिएट कंडीशंस वाइज और फॉल इन जनरेशन और लोड होता है, और उसके लिए ये जो हम लोग का बैटरी एनर्जी स्टोरेज सिस्टम, पंप स्टोरेज सिस्टम, these things play a vital role. Okay, so that's now I think the foundation of why these storage systems play a part is more or less, at least you have a rough idea what's the need of using this battery energy storage system or pump storage system. Anything you need to, you have to, any questions? Okay, Okay, then let's move on next part. That so what we have right now. This is from the lecture itself. You can definitely go. Already you have gone through, but just a brief overview. This is the evolution of how this thing, the each and every batteries and all these things have evolved. So I'm not going deep because just you have this idea and you can always go through the lectures. So location flexibility, storage devices. This is the point that I have emphasized. Decarbonization. So that's the aim because we have increased DERs in place. So and with the DERs in place, the variability, the intermittency have increased. So for that thing, we need to take care of this. So power injection, of definitely power injection, controllability, flexibility of this entire operation gets enhanced. Okay. So types of energy storage system. Here are some categories like thermal energy storage system, mechanical energy, chemical energy, and electrochemical. So here we have this thermochemical energy. So this you can definitely get any idea of how the pumped hydro power plants work and how they get. There are some. What I would say is that there are some uh, tariffs that are only based on these hydropower plants if they can maintain some frequency within prescribed limits. So any idea how these pumped hydropower plants work? Battery, you have idea? Anything you would just feel free or right. Okay, so okay, let me discuss here itself. So you have a upper reservoir, okay, and you have a lower reservoir. So here you have an upper reservoir and here you have a lower reservoir, upper dam, lower dam. And whenever there is a main aim of this entire purpose or the entire purpose of uh, making this grid working more smart, acting more smart. One part is that it is mostly related to how the communication infrastructure is developed nowadays, and also how the what I need to say is that mostly our aim is to have a continuous power supply. That's our major aim. The sometimes in previous means 5 to 10 years back, we used to face much more uh, power outages. So our aim is not to face these power outages more. So based on that, and how would we not face power outages in a larger scale if we can maintain the frequency within the limit? And how the frequency can be maintained within a limit? That can be maintained by regulating the load and generation balances. Okay, so with the DERs in place, intermittency has already encroached. So we definitely need to do something extra to have at least upper hand of the operating scenario. So for that we are keeping spinning reserves, battery energy storage systems. So spinning reserves, I'm trying to say is that storage systems like battery energy storage system which are fast acting. We can definitely have storage spinning reserve as a secondary unit of a power plant not operating in not in a not non-operating mode or operating on the lowest uh, power that can be delivered by that unit, but everything should be fast acting. So to make this thing fast acting, this power pumped hydropower plant they can come into action within roughly you can take around 5 to 7 minutes. I've seen power plants means my training days. So there they come into operation within seven 7 minutes to the full load condition. Okay, they get synchronized within 3.5 minutes, and after that, these power pumped hydro power plants. I'm talking about pumped hydro power plants. Okay, so and after that they uh, just deliver their full loading condition, and the not that full loading condition is definitely quite high. Means it's around, you can say, 200 megawatt. So for that 200 megawatt, you will have to have the upper dam filled. Okay, so there are sensors. So again, these sensors come into action. Okay, so based on these pumped hydro power plants, they deliver the amount of energy during the daytime, mostly during the peak hours, not in the day or night, that I won't classify them like that. Mostly during the peak hours when the thermal power plants are base load power plants. Okay, and with the DERs in place, the intermittency is increased. Now, along with that, if there are sudden imbalances that needs to be catered within fast faster time scale, for those things, this upper dam is opened, and the rest is the operating principle is same. But during the off peak periods, they can, from the lower dam, the synchronous generators acts as synchronous motors, and they pump the water from the lower dam to the upper dam. Okay, and that's the major advantage, that what we are aiming is that, next we will also discuss that part also, that we have a we have these load curves like this, a morning peak and a evening peak. Okay, so our aim is to minimize this and increase this, so that we can maintain a flatter profile. So if we try to maintain a flatter profile, that would definitely, means we can definitely maintain a flatter profile all throughout the day. But for that, various activities needs to be performed. Like these pumped hydro power plants do participate in maintaining a lumens. They generate or they deliver power during this period, so that these thermal power plants can, this is the load curve, so this thermal power plant generation can be reduced. And again, during the night hours, this is the not in the night hours, off peak period, load off peak period, they pump the water from the lower dam to the upper dam. So for that they need energy, so here the load gets increased. Okay, so here the load gets increased. So they are, what they are doing is that they are enriching the load curve, or not enriching, I would say, I would try to say is that, with the what's the with the aim of these operators, means the load curve is shifting towards the optimistic side, means on the optimistic side for the operators or the distribution system or transmission system operators. Okay, so here we can see the classification of energy storage system. So it's from the niti.gov website. So we can see that mechanical, we have pumped energy storage. Then we have the compressed air flywheel. Or electrochemical, we have batteries, various kinds of batteries. Thermal, we have these three. Electrical, we have supercapacitors, superconducting magnetic SMES. So these are the classification of energy storage system that aids in maintaining the power system operating balance. Okay, the frequency operation, operating frequency to be kept within range. Okay, this is the energy roadmap. I'll share this slide so you can get the access to this PDF. You can see that how much the rooftop solar has increased. And this is from that website only. This is the aim for 2027. Okay, so this is again from the slide, that the we have this aim, that energy shifting. So what's the aim of energy shifting, and what are the energy shifting procedures? What's that term known as the mechanism of energy shifting? So what I'm trying to say is that the energy shifting is mostly done to, we have a load curve. Okay, so what's the load curve? The load curve looks like what I've shown you previously. Now with our aim is to flatten the load curve. And what's a load curve? It is a load duck curve, it is also known as. But again, another major thing is that if we have the solar generation within the daytime. Okay, so what we can observe is that we will discuss in the next slide itself. We have that part. So here we can see that energy shifting means they should act as capacity reserves, right? And discharge during the peak hours, and also to charge during the off peak hours. So what I have presently, lastly, I've told about the pumped hydro storage system. Same goes for the uh, battery energy storage system, right? So for the batteries energy storage system, during the off peak hours, the batteries should be charged, and during the peak hours, they should be capable of delivering power to the grid. And in this way, they can maintain the frequency of operation. Okay. So also the congestion relief somehow, if there are too much loading on the line, so some power needs to be absorbed beforehand, so that, and who can absorb? If someone has the facility to absorb, they can only do that thing. And the batteries do possess that capability of consuming or storing that amount of energy. So system operation. So this is the system operation. Let's, for the system operation, we have these three parts: frequency regulation, flexible ramping. So faster ramping should be done. So this is these things I have discussed, that the aim, but this is on a compact form. But the overall discussion we had, that our aim is to have faster response to the frequency deviations we have discussed. Again, our aim is to flatten the load curve. Again, we can provide black start services. Okay, so suppose there are outages. Oh, anybody have any idea of the 2012 outages, 2012 uh, uh, blackout that happened? Are all of you aware of 2012 blackout that happened on this in India only, on the northern grid, western grid? Anybody have any idea about how the blackout happened? So majorly, the blackout happened on the, because the line overload limit means there are some overload limit, right? The lines which can operate around, let's consider 10 megawatt, is, let's suppose, means it's not it's a rough value. So if we have a 10 megawatt line, okay, if that can line can carry 10 megawatt, there is some overload limit, that 1.5, let's consider 15 megawatt it can carry at max. But if that overload limit also gets violated, during those cases, with thermal overloading, thermal breakdown happens. So based on that, the line, based on those increased overload, means increased line power flows, the breaker trip means the first breaker trip. So it was, I think it was taking part to Gwalior, I think. So first line trip, and after that the second line trip, and in this way there had been a cascading of events. Means since first line was overloaded, then second line also gets overloaded, and in this fashion, each and every line got overloaded because suddenly, if one line trips, everything is interconnected. So that power would flow from another line itself. So on which line would it consider? The parallel lines that would be operating. So eventually they got overloaded. And based on those overloading, again those lines got tripped. And in this way, a cascading outage occurred, and that led to this 2012 blackout. But initially, uh, the initially yes, the eastern and the eastern and the southern grid was not there. Eastern and northeastern grid was already in place. So already islanded themselves. But the southern grid was not connected during that time. So southern grid was safe. But eastern and northeastern grid islanded themselves. But after that, the western and northern grids was totally outage. And after that, when the after rectifying those problems, and again on 28th, I think, or 29th, 28th, I think. So again on 28th, oh sorry, or 38th, 30th of July, 30th of July. So again, when the entire grid was tried to be synchronized, again four of these grids, four of east, west, north, and northeast, all these four grids were outage altogether. The southern grid was there also. The southern grid was islanded because they didn't have that during that time. One grid, one nation, one frequency was not there. Okay, so southern grid was different from the east, west, north, and northeast grids. So the main point is that we need to minimize those outages, and as early we can go through these monitoring actions. Means how can we minimize those outages? We will have to emphasize more on monitoring actions, and who are these? What are the devices that helps in monitoring the power systems? We have the SCADA, we have the PMUs, we have these. We can say nowadays smart meters, everything. So monitoring actions and delicate devices with higher accuracy should be present to deliver this is to deliver better control. Okay, so what I'm trying to say is that we need to have more control or preventive measures to operate the present grid, because this grid has now become much more vulnerable. So the power system engineers are more aware of the power system side, but since they have integrated the control communication part, the IT part, billing and everything. So attacks and all these things are attacks means cyber attacks. All these things have become much more. Uh, there are much scope of these things to happen. Okay, so Ukraine attack 2019, I think. Okay, the malware and these things do get injected, but these things are based on only the scope that we are trying to enrich our power quality, but we should not increase or enrich them on a cost of harming ourselves only. So everything needs to be taken proper care of. For that, these battery energy storage systems, they also have some pose the major advantages, but they also have some disadvantages like the cycle life of battery, the second life of battery. People are doing research on those part also. And so again, this part PV and generator. So we were discussing something different, but related to smart grid itself. Now we can see that system operation we have discussed, the investment deferral. So suppose a line is carrying overloading, line is getting overloaded. So for that we need to divert them. So for that the congestion relief action can be made. So batteries do take part in this congestion relief part. So another thing is that are you aware of the demand response activity or demand response activity? Are you aware of these demand response programs that do take place in the power systems? Demand response, any idea of demand response?
Sir, demand response is acting on the tariff. Like if we the consumers are uh, given an opportunity to consume less or more based on the dynamic prices which are available on the grid, and they are made informed through the smart grid or through smart metering.
Hmm.
They are uh, promoted to use the more electricity in case of extra availability of power, and in case of less shortage of power the power is made costly and they are discouraged to use the power.
Yes, 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 yes. Thank you. That's the main aim of demand response, and to promote this demand response, at least nowadays, they one major difference that you can point out. Can you anybody of you can point out between the previously operating power system and the present operating power system related to the customer level? Any major change that you can observe?
Sir, there are changes like introduction of consumer act. uh,
Yes,
Also there are changes related to introduction of TOD tariffs.
yes, yes.
Also,
Time of the
there
detail.
is increasing shift on transition to renewables.
Yes.
So, cheaper source of electricity like solars are now, which have less tariff than the conventional ones.
So yes, so they are more promoted to the customer level because nowadays countries where we can observe in Australia, they have made it mandatory that each and every house will definitely have a solar rooftop. They won't be spared. Means each and every house should be having their own solar rooftop. So uh, because with this thing in action, because we need to, the main aim was what I'm trying to say is that the customers are more emphasized, means the priority of the customers gets emphasized nowadays. It was not the same as the conventional power system in operation where the unidirectional, because during those time the operators or the generators were the controllers in the entire power system. Now it's now the customers, based on the willingness of the customers, the generator will have to deliver, and also the customers will to means they have their rooftop, they have the various kinds of uh, devices, or let's suppose refrigerators, air conditioners, all these things. So they operate on their own, but the demand that needs to be fulfilled is based on the customer's will, because if the customer is willing to, means they have their electric vehicle, if they are willing to deliver that power to the grid, they will have the activity. Nowadays in India we can't foresee that much amount of electric vehicle charging station. That's the major reason that people are still keeping them devoid of using this power, using the EVs at a much means extreme level. Because if suppose I'm willing to go somewhere in Bangalore or from Kanpur, so I can't foresee that each and all throughout the way I would be equipped with uh, charging stations. But in Australia, recently, from one of the professors I've met, so what he told that they, yes, whenever they are going somewhere, let's suppose they are going a distance of covering a distance of 500 kilometers. So if they are willing to charge, their direction would be, means their way would be directed in such a way that they would find a definite EV charging station. And if there is no EV charging station in that route, and based on the battery SOC of the EV, the battery SOC, if there is no information that in that way they won't get any EV charging station, and the amount of charge which is left in that in the EV won't be sufficient to traverse that amount of distance, so they won't allow the person or uh, whoever is a driver to drive in that direction. Means the app based or app monitoring systems are quite high, means quite enriched, and they can also deliver power to the grid. Means V2G is already in action in their country, but now we don't have that much infrastructure, but definitely surely on the upcoming 5-10 years we might see a major change. Already the public transports are getting transferred to the battery, means electric vehicle side, but and these entire things are emphasized mostly on the customer end, means how the customers would be controlling the powers, means they have become consumer as well as the producer. So the prosumer term is now more appropriate for the customers. Okay. So and the demand response, coming to the demand response activities. So what you have rightly pointed out, they are given incentives to minimize or curtail the power. So one important thing is that for these smarter grids uh, to be in operation in any of the countries, not only ours, means in any country or any place, the customer should be at least uh, they should have an idea what they are willing to do. Means if the customers are the participation of the customers is a major chunk that we are not willing to do any kind of outages. What we are trying to say is that just have some, means they would be informed based on the smart meters apps or all these things, they would be informed that these things needs to be done, but at least the customer need to do that. So they shouldn't be reluctant, and that's the only way we can make that grid smarter. So the customer participation is a major chunk, so that needs to be taken care of. So coming back to the energy storage system again, so we can do is that what we can do, these are things that we have discussed, that frequency regulation, capacity farming, so grid investment deferral, so these things we have discussed. So it is the India's battery energy storage scenario. So 37 megawatt hour of battery storage capacities currently India has. It's a bit you can consider data, it's not exactly at this time frame. So according to the estimates, the power sector is planning to it requires 236 gigawatt hours of battery energy storage system in addition to 27 gigawatt of pump storage. So pump storage projects, they need area, so geographical conditions. So to Indian forest what's that called, forest department. So forest departments also has some rules that mostly the pump storage can't be placed somewhere anywhere in the localities or public places. So they has to be on a remote parts. They has to be uh, structured on a remote location. So that they are the mostly the people in human intervention is less. So or there is not any public movements there should be minimal public people staying there, minimum people staying there. So what I'm trying to say is that so to acquire the land, but they need to destroy the trees, they need to cut down the trees. So for that, forest act also has some rules that they need to plant trees. So so the number of trees that they would be cutting down, so those number of trees should be again planted. So things are not quite easy for the pump storage part, but yes, government is trying to do all these things in order to make the entire power system move or aim towards smarter energy grids. Okay, so with the control, monitoring, and control action in place, so these are the terminologies that you can directly get: energy density or density. So response time, cycle life, these are directly taken from the yeah, on the lecture slides itself. And the prospects, transfer and distribution, upgrade deferral, voltage regulation, frequency control, ramp rate. So another important thing what I missed is that uh, the okay, let's here. Wrong somewhere. Oh yes, here. So what I mentioned here is that load. So you all are aware of power system stability, that which kind of stability needs to be addressed at which point of place. So any idea what kind of stability means? There are many stability problems, frequency, voltage, and all these things. So rotor angle stability, all these things. So what stability now also DER integrated stabilities are also in action. So any idea on what stability should be maintained on the voltage, sorry, load side? Any idea?
So there can be reactive power compensation.
Ah, yes, reactive power compensation is associated with which kind of stability?
Reactive power demand at user
Now,
level.
user level definitely, but I'm trying to say is that there are some classification of stability, right? So, you this reactive power support is given on which side? Means I'm trying to say is that on the means there are two terms. Means the real power
Supply
is,
side and demand side.
yes, supply
Demand
side, and
side.
yes, the reactive power is support given on the demand
Demand.
side. Now for the demand side, the associated stability problem is the voltage stability issue. Okay, so the mostly the voltage stability problems we can observe based on the uh, means we need to take care of the loads, means or we need to give provide active reactive power support so as to maintain the voltage stability problem, means to as to address the voltage stability, not to maintain, I would say rather. So with using these energy storage devices, we can also maintain that voltage stability, means we can at least try to maintain somewhere, although they would not deliver the reactive power support in a fashion that these fax devices, they are much more proactive, means they can change. But yes, definitely base these injections can be changed using those fax devices itself. So frequency control, voltage control, and all these things can be taken care. Okay, so now coming to the duck curve. So this was the point what I was trying to say. So we have two peaks all throughout the day. So it's morning peak and evening peak, but with the renewables in place. So here what I was trying to say is that renewables are mostly we can observe solar. Considering the Indian perspective, let's consider, because wind is not, yes, wind power plants are also there, but the percentage of wind power plant is not that much. Means it's 9 to 10%, whereas for the solar it's 25 to 27%. So mostly governed by the solar power plants. So now if we see that the duck curve here, this is going down with years. Okay, so this is good that this is going down, but at least we need to take this thing down again, because this is the peak part. So that peak should be minimized beforehand. Okay, so nothing much to discuss on this part. Again, this is the energy storage system. This is directly from the lecture slide itself. You can find the operating losses, inverter losses, switching losses, all these things. Again, the this is the equivalent model. So based on the more number of RNC to be encountered, if we can, means the more accurate model can be replicated by more number of RNC to be channelized in series in this fashion. So that would give more accurate a model of that DESS. Okay. So SOC, state of charge, DOD, depth of discharge, it is, we can observe that 0%. This is 0% DOD, what means 100% SOC. So 1 minus that part. So this is allocation part. Allocation part is mostly you have seen that how this battery energy, this is an optimization problem that has been addressed. So to see that, to find out the position or to find out the nodes by placing the batteries, the battery energy storage system in those nodes, how the voltage means our main aim is to flatten the voltage profile or to take the voltage profile towards their higher side, on the higher side, means not to go beyond the point 5% reduced voltage. So that's our aim. So what we have found is that in that lecture only you can see that it's a problem. So these are practical problems that needs to be understood by programming all these things. So this is the workflow how the practical problem was solved. You have seen in the lecture itself, just to give an overview what were discussed in the entire week. So these are the applications of lithium ion battery, and it's the battery choice. So specific energy density, and on this side volumetric energy density. So based on that, lithium ion is most suitable. And yes, SOC estimation part, the state of charge estimation needs to be taken care of because with the various techniques, conventional techniques, adaptive Kalman filtering techniques, machine learning and deep learning. So you can observe that a lot of work is going on this adaptive Kalman filtering technique, machine learning, deep learning techniques. So they are mostly with the help of these estimation techniques. What we are aiming to find is that how these uh, entire, what's the operating condition, present operating condition of these batteries, okay, and what are the inputs. So inputs are voltage, temperature and current. So these are inputs, and output is SOC, SOH, or fault status, whether it's on or off, or what's the present condition, okay. That's the BMS. It's the structure of, it's the head, or the, likewise for the power system we have the uh, control room, or the SCADA, which is also known as the brain of the entire power system. So this is the SCADA is the decision making entity. So here also BMS is the decision making entity. So cell balancing, we can see that some cells, none of them can be ideal. So for those cases, uh, at least cell balancing should be done so as to make this point of operation same for all, okay. So and this cell balancing, based on this cell balancing, the discharge and recharge rate of these batteries would be uh, same for all, means the rise and fall of this energy or charge storage capacity of the battery should remain same for all. The rise or fall should be same for all. So that's the purpose of using cell balancing, so that if some one battery get discharged but still the others do possess the charge, so in these cases the things would get the batteries would, the cells would get destroyed. So for those cases, yes.
Sir, how it is done? Like how we can balance these batteries,
Yes,
same charge.
that's yes. So cell charge balancing. So we have this battery energy storage system, means the system of the controlling action. So we see that charge estimation. So based on this charge estimation, what we can observe is that what's the present operating status of the entire battery, or what we can say is that battery bank. Okay. So now let's consider the case that we have various techniques like this active cell balancing, passive cell balancing. So based on those active cell balancing and passive cell balancing methods, we can find out that how this battery, these are mainly, we can say, some design aspects that we need to take care of initially, so that this battery, means the aim of cell balancing is the all these four batteries should have the same amount of charge. and one battery is having lower charge, another is on the higher end. So that would depreciate the life cycle of the entire battery pack. So the main ones, how it's done, you can find out that there were various cell balancing techniques discussed, like what we can say flyback controller converter based. Some methods were discussed, and what yes, like let me. There were some methods. Let me flyback.
Also, this
Uh,
battery management system has some control algorithms or some
yes, yes, yes.
controllers, microcontrollers.
Yes, they have the microcontrollers. The program is to be embedded on these microcontrollers itself, right? So this is the battery management. Suppose this is the entire battery pack. Okay. So on top of that, you have just these are let's suppose the series parallel combination. So here the series parallel combination of the battery pack, right? So after that, let's suppose these are the terminals, and based on these terminals, the input condition would be varied for all these batteries or cells based on the programmable microcontroller. So there has to be a microcontroller that controls the operating conditions, and the operating conditions is governed mostly on the program. We'll have to program like we discussed that the conventional method, adaptive Kalman filtering. These are the estimation, state of charge estimation techniques. So likewise, we need to dedicate a different part. Means we'll have to program the based on likewise. If suppose this is the data, so we can program based on there has to be some feedback loop. Okay, so for each of the battery or each of the cell, the feedback needs to be observed that this is the present status of the battery, and based on that, that battery would be kept constant, because an ideal operating conditions all should go down or go up, but in practical cases that is not the operating scenario. So for that, this microcontroller, the programs are to be embedded, and based on that, there has to be some let's consider some inputs, or the status can be monitored based on the data that is received, and there are some threshold values, beyond or that threshold or lesser than that threshold, the operating conditions would be what would not would change for each of these batteries in operation. So means we'll have to maintain the cell balancing with by embedding some program itself along with some hardware equipment. Okay, so microcontroller is the head, so that will direct um, the means the flyback controller based operation or bidirectional flyback controller, etc. Means there are some modes of operation, so that they would the microcontroller would sense first, and based on the sensing, they would dictate that commanding action to be performed on the battery on the entire battery system or battery pack, and after that, based on that, the reaction would be or the result or the outcome would be uh, smoother rise or fall in this battery charges, means the charging or discharging of the battery. So yes, definitely they are programmed, but
Okay, sir.
okay. So that that's the overview of today's discussion. So if you are willing to participate in this small, we have also the last. Okay, so this is the some basic questions we can discuss. You can write in the chat box also, and also I have some few more questions from the previous years question papers. It's not the question papers, I would say assignments, but you don't have the access to those assignments right now. But since I have them, so I have collected, and that would be based on. So based on the how the time permits, we can discuss more questions. So for the timing, let's start answering one by one. Means anyone can you can write I think it's visible.
Yes.
Okay.
First is compressed air. नहीं,
First is
latent.
yes. Latent is the answer. Latent is not. Next, not feasible. Please emphasize on this point. So, energy storage are not feasible for hybrid energy storage system. Not feasible. कौन सा इस पे not feasible है to be part for hybrid energy storage system. Any rough guesses?
So super capacitor and battery.
They are part. So here the answer is none of this because all the three can be framed. Okay, so they are feasible. So so now for this one, I think it's visible.
Yes, sir.
Yes. So
So it's a C, third option.
yes, it's C.
Lithium ion battery.
Twelve volt battery of capacity 500 ampere hour, 80% SOC. Depth of discharge is required.
So 20.
Yes, 20. DOD is means in percentage definitely. It's 1 minus, or sorry, not 1, 100 minus SS.
400.
Yes. 400. Distribution network planning problem. It was directly, this question is directly from the, lecture.
Non-linear. As it?
No, not non-linear. Yes, it is non-linear, but something more along with non-linear.
Like mixed integer, this programming is also used in power market.
Yes, mixed integer non-linear programming is also used in power markets. So here also it's mixed integer non-linear programming, MINLP.
So what is actually what is this?
This is mostly the distribution system planning problem where you can see that uh, you are equipped with, let's suppose a distribution system. You have the nodes here and let's consider more nodes here and there, and that would continue to an end. Okay, so now we have, so the question that, or the, sorry, the not the question, I would rather say the problem that was discussed in the lecture, that was uh, discussed for a 33 bus distribution network. So 33 bus distribution network where the the loads along with the DERs, and the battery energy storage system. So everything with everything in place. Now we need to find out. So we have the total power demand. Let's suppose we have the power demand X. Let's suppose X megawatt is the demand, and we generation is Y megawatt. So this was normal operating case, but now, sorry, no, normal operating case is only the demand part. Okay, but now we have a generation of y megawatt, that is due to the DERs or batteries and all these things. So for that we have a net loading scenario. So now the question was, or the distribution network planning problem was, we have DERs at some locations. Let's say here we have a DER, here we have a DER. So based on these two DERs placed in these two nodes, what would be the batteries that would be placed so as to obtain the best voltage profile? Means the voltage profile that we can see for 33 bus system is slightly like this. Okay, so as we go, this is not 33 bus system, so that would be different. So what we can see is that, so the voltage at the substation node is somewhere here, but as we go towards a node, because the network looks like, let's say the network looks like it has some nodes here, it has some nodes there, and based on that it also has some nodes in from there. So it's a general idea, it's just a rough, but it's not balanced on both sides, right? So the voltage nodes are mentioned, or nodes are named here, the node based on the node numbers, and if we have the voltage magnitude profile at each of these nodes. So what we can observe is that as we go down, let's suppose on this lead blue, on the highward side, if the node values voltages, so as we will go towards the load side, the voltages would dip. Okay, so in the substation node we will have the highest, because we have the regulator, we have the highest node. So sorry, highest voltage here. So that is the voltage at the substation node. So as we go down here, we end somewhere, again we come back to this part, so again the node voltage rises to somewhere, because the value of the voltage is higher here rather than what is here. Means here if a node voltage node, this node is for this node, let's say n. So this is the for node n, but again here it is a, let's give it, rename it as b. So here it is starting for a, and here again it is starting for b. So here we would get the voltage profile, and our major aim is to improve the voltage profile. Means if we can improve the voltage profile, let's say uh, if we can make this voltage profile this in this fashion, So that means we have increased the voltage profile of or made the voltage profile better, because our aim is to provide a good quality. Means in the distribution side, what mostly we face the voltage issues, right? So those voltage issues can be mitigated by properly placing the DERs or properly placing the batteries in place. So this becomes a distribution system network planning problem. So how these things should be planned so as to have the best possible voltage values, means beyond that it is impossible to reach, because as we will go down, means from this side to this side, definitely there will be a voltage drop. But if we can place now this can't be a case that we would be delivering a huge number of DERs, or we will be placing huge number of DERs. So that is an optimal choice. There has to be our optimal choice. So the problem is optimal sizing of the DERs and optimal sighting of the DERs. That is how these where how would what would be the magnitude of these, the magnitude of power that is will be delivered by these DERs to the grid, and what will be the position or the places that where these DERs would be placed. So this becomes a distribution network planning problem, and this can be solved by MINLP.
Sir, in our case,
Ah,
suppose a feeder is terminated and there are consumers which have solar rooftop, like government is promoting through
yes, yes.
a scheme. So, will this cause problem or
So that won't cause problem, but with that in operation, because each and every d years with each and every d years, more number of constraints would be increased. So the operating time wants to find out the optimal position and location and sizing of these d years or the battery banks. So that would become, means optimal choice of both the size of the DERs, means the generating capacity of the DERs, as well as the location of these DERs. So now if we are fixing the location of the DERs, so what would be the optimal choice for the the optimal generation that would be that should be delivered by these DERs? Now it becomes a question. So means we are somehow the problem is getting more complex, but it won't be this won't be case that the problem isn't solvable, because we are placing DES in 4 nodes for a 33 node 33 bus distribution feeder, node distribution feeder. So in that case, if we replace that 4, means if we increase that 4 to 8, because government is promoting, that won't cause any problem. That would rather improve the voltage profile. Definitely it would improve the voltage profile, because then the demand that need to be catered by the substation node is a difference between this x and y. Okay, so the y, if y is getting increased and the load is staying same, so there the voltage profile would definitely increase. Means increase in the sense would get better, means this curve would rise a bit high, means it would go like this manner. So there we can observe that the voltage profile gets increased beyond this blue line also. But the
sir,
problem,
but there can be exceptions like uh, government is promoting and everyone has a rooftop solar.
yes,
And
yes,
suppose there is a cloudy day, there
yes,
is not enough generation by this DRs, and
yes,
there is the load remains the same, or it dips by only few percentage as compared to the generation dip.
yes.
So in that case, but then
Yes,
there will be a
yes,
pro-
that would cause problem. But the problem here that we are discussing, this problem is being addressed with the maximum generation capability in taking into consideration. Means, suppose a PV is installed, it can generate a maximum of 2 kilowatt. Okay, if rooftop, let's consider a rooftop. Okay, so that rooftop solar can generate a maximum of 2 kilowatt maximum. So this problem would be considered, this generation or this optimal sizing and sighting problem would be considered For that considering that maximum generation capacity into taking that maximum generation into consideration, and not present operating condition, yes, that would definitely deviate from the maximum. But if we are equipped for the maximum, then that that the let us, if we can observe that, let's say that we are prepared for the most, at most this is the limit, so we are prepared for this point of time. So now if we consider for this range, means let's suppose we are equipped with our optimal location and sizing and sighting with only this much range, so we are equipped with this much, but somehow the generation increased to this point, so that there would be a definite voltage increment or decrement somewhere which is not previously considered, and if that value goes beyond the prescribed limit, then definitely they would face major outages. So for that planning problem, so this problem is considering the maximum capacity. So if the maximum generation capacity is being taken into consideration, then the intermediate or the reduced point levels would definitely not cause any problem. But if we are equipped for this level, and if the condition comes as this one, then definitely there would be problem somewhere, and we won't be aware of that problem, and something outage and all these things might take place. So this problem, what you are trying to say is that, mm, on suppose today is Saturday, tomorrow these things might change, Monday this thing might change, yes, definitely it will change, but which should be equipped for the maximum operating. This problem is based on the maximum generating capacity, considering the maximum generating capacity. So maximum size or maximum size should be taken care of. Anything else?
Okay, sir.
Means, have you? That's what I'm trying to say. Have you understood? Means definitely it would be a change, but considering the maximum operating condition into this problem, so this can be the output of this load profile or voltage profile would be the out voltage profile for the maximum limit. So nothing can go beyond that. So considering that part, this problem is being encountered. That is the distribution system planning problem. Is it okay? Or
Yes, sir. Yes.
okay, okay. So next question.
Is it a global optimal solution?
Yes, it is global optimal solution.
Is it a damage to the SEI layer?
Yes.
Specific gravity of electrolyte?
Yes. Okay, so here these questions are over for this week, but we can discuss a bit more about few questions from the previous week. So these questions, uh, you don't have access, but it would be more related to the last 2 week lectures. So that has been done by the professors. So I'll just write some points, means not the entire question, so that the meaning gets delivered. Okay. So if you are willing, then I can start.
Yes, sir. Sure, sir.
Okay. Thank you. Thank you. So 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 one question is environment friendly. environment friendly, DER. So you have four options. Uh, One is IC engine, V is gas turbine, C is fuel cell, D is geothermal.
So is it geothermal?
Environment friendly. So can be geothermal, but a more environment friendly would be fuel cell rather, I would say, right? Okay.
So geothermal is considered as a renewable source. So we
Yes, it is considered as a renewable source. Yes, definitely. But the main aim was environment friendly in the sense the output of fuel cell we get is water.
okay. Sorry, geothermal cannot be DER.
Yes. So how can it be considered as a part? Yes.
Okay. Okay.
Okay. So okay. So coming to the next question is which of the following provides uniform information exchange? Uniform information exchange for monitoring and control of wind power plants. Wind power plants. Okay. So A is so all would be IEC. Okay. So let's club that IEC plus two would be IEC. So IEC part A is 61400025 and part B is 61850 7.420 and next two are from the IEEE standard. So C is 1588 and D is C37.238. Monitoring and control of wind power plants.
It is IEC 6140025.
Yes, 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 it is. It is. So, yes, again, IRIGB. According to IRIGB, time synchronization, time sync requirement is a zero point 0.5 microsecond, B 1 microsecond, C 2 microsecond, T zero point 0.1 microsecond. So
Is it
anything?
point 0.5?
No,
2.
no, it's not true.
So I am completely blank about this.
Okay, okay. It is 1 microsecond. 1 microsecond. These are standard, so it is 1 microsecond. Okay. So next is in advanced metering infrastructure. I'm not writing the entire sentence, so I'm just in advanced
Yes,
metering.
sir.
Yes. So
Actually, I am working in AMI from last 6 years.
okay, okay. Then you would be more knowledgeable in this domain over me. So okay, no issue. So here. AMI we use some protocols. So it meter uses the protocol. So UDP, IP, Internet Protocol, and TCP and all.
So TCP is mainly used, but it can be all. TCP is mainly used,
TCP IP, yes, that protocol
but
is.
all TCP IP for data
Yes,
exchange.
all would be more appropriate. Okay.
UDP is also there. There are two.
Uh,
In TCP, there is a confirmation of information, whether it is
Acknowledgement,
sent or not.
acknowledgement.
Acknowledgement will be there. In
Yes.
UDP, I thought it is
For,
UDP. UDP also, there will be no confirmation,
no,
acknowledgement.
no acknowledgement status. Yes, from the UDP side. So now, so this question now, yes, which component of SCADA presents data to the master station? I think this question was there in this
Yes,
week
sir. Assignment. It was there.
assignment. It was there in the assignment. So DPA, RTDB, DTA, and DCA.
DPA. DPA.
Yes, DPA. This question was there. I
Hmm.
also, after seeing that, I also remember. So, acha, power range for industrial loading. So,
25 HP, more than 25 HP.
no, power for industrial, no? That was
200, more than 200.
yes, more than 200, yes,
SIP for SIP is better.
uh, more than 200. So, another question is that IEEE standard conformance test procedures for equipment for interconnecting. This question was also there for DER integration with power system. I'm just writing that in examples. I sorry, options. Means IEEE standard. Is it audible, right?
Yes, sir, it is.
Yes. IEEE standard for DER integration uh, with power systems. So all are IEEE. So I'm not writing IEEE in front. So 15471, 15472, 15473, and 15474. There are four. So
It was three, I think. It was three or
uh,
one.
one was the answer. So DER was for one. So yes, so,
Actually, there are so many standards, so
yes. Sometimes
I
this
don't.
protocol to remember all these protocols becomes difficult.
Yes, sir. Confusing also many
Uh,
times.
yes, but the people those who are working on this,
Working.
yes, they
For
are
them
much
it is
handy. They
like
always
for AMI we have 16 444 15959.
yes.
There are
Six
like
one eight five
IC
zero 61850 is also for I think smart metering, right?
61
Oh no, sorry,
IC.
that is RTU. 61850 is for RTU, and for smart meter, I think DLMS uh, COSEM protocol is also followed.
OSM
Yes,
15959.
yes.
And
Okay,
there are
that's it.
IEC also. IEC standard is also there.
IEC standards are also there.
Mm.
So those are much more handy for the people who are working regularly on it. But
Uh,
okay, that's it. And these were the questions. So next, these were from the previous year's assignment. So some coincided with this year's also. But still, I tried to take those things into consideration. So yes, that's it from my side. And
Thank you, sir. But I just want to have if there are some advancement related to AMI, so can you share your number or
okay,
uh,
then okay, let me just switch off this recording. Okay, this is recorded.